Hello friends, in this lecture I would like to explain another example based on the beams. See here, a simply supported beam ISMB 400 has an effective span of 5 meters. So just what is the given data? So the given data is they are asking to design a beam. So that is design bending strength of beam, design shear strength of the beam, and intensity of the UDL that the beam can carry under service condition, and what is the maximum deflection for ISMB 400. So this is the weight. Actually it will be there directly in the tables also. I will show you now. So this ISMB indicates Indian standard medium weight beam. Okay, so already I solved one small basic example in the last lecture, so you please watch that one. So here also same way we are finding the properties in the steel tables. See here ISMB 400 where it will be in the steel tables. So see here, this is the steel table and the two rolled steel beams in page number 4, MB 400. So ISMB 400 in page number 2. So this is the ISMB 400 which is 61.6. Actually it will be given in question also. ISMB 400 at 660 Newton per meter. So you can check all the properties, whatever the properties you want. There will be H, B, TF, TW, IXS, IYY, RXS and RYY. All the values will be there in the steel tables. You write down all the values, whatever the values you want here, and later you can substitute in the formulas. So first they are asking about the design bending strength of beam. So first one is design bending strength of the beam. So for finding design bending strength, so what is the formula? So actually the formula will be there in the code book, page number 53. So I will show you. See here in page number 53, the formula will be the design bending strength of the beam. MD shall be equal to beta B ZP Fi by gamma m naught. Okay. So I am taking the same formula here. MD will be equal to design bending strength will be equal to beta B ZP Fi by gamma m naught. So where you will get this ZP? This ZP will be obtained in the steel table directly for ISMB 400, and Fi is here we are assuming Fe 250 steel, which is Fi will be equal to 250 Newton per mm square. And what about gamma m naught? So gamma m naught will be taken like same in the previous example, okay, which is laterally supported. You will get 1.10. I told you in the last example itself. And what about this beta B? You check once here. This beta B will be equal to 1.0 for plastic and compact sections and ZD by ZP for semi-compact sections. So first you can confirm whether your section will be in the plastic or not. Okay. So first we will go for the trial section. First section classification. So first section classification. Again you can check the code number, page number 18 for section classification. See here, this is the table which is related for the section classification. See here, class 1 will be plastic, class 2 will be compact, class 3 will be semi-compact. Means for rolled steel sections, I am checking with B by TF will be less than 9.4 epsilon. See here, B by TF less than 9.4 epsilon. First I will check with this condition in the compact plastic section or else in the compact section. You check any one. First one, B by TF. I am assuming this case and again. So here, what is this epsilon value? You can check here, code book itself. 250 by Fy whole to the power of 1 by 2. What is Fy will be given in our, we are assuming Fe 250. So 250 by 250 will be 1. So power to the 1 also 1 only. So I am telling like this. They are giving epsilon will be equal to square root of 250 by Fy. So Fy will be taken as 250 only. So 250 by 250 which is 1. So therefore I am taking directly here 1 itself, and less than B by Tf. So B by Tf. And again you can check the condition for B here in the next paper, which was in page number 19. So your B value will be exactly taken half of the flange, taken from here to here. In this case, in the built up sections, if you take C means it can be taken center to center. Again, what is BF? BF will be the internal elemental width. So generally your BF by 2 will be less than 9.4 epsilon. So if we are taking BF, so how many times you are taking this one? B will be equal to this BF by 2. Okay, so this B will be equal to BF by 2. Why? Because B will be exactly half of the flange and this BF will be full flange. Therefore, 2 times of B will be equal to only 1 times of BF here. Therefore, B will be taken BF by 2, because this is the outstanding element of compression flange. Therefore, this B will be equal to BF by 2 by thickness of the flange, check then less than 9.4. Okay, so what is BF here? So the value of BF will be, see in the steel tables, steel. So where is BF here? BF will be breadth of the width of the flange. So for IS in this line 140. So I am seeing here 140 for ISMB 400. So I am taking directly 400 140 by 2 by thickness of the flange. So again, where is thickness of the flange? So thickness of the flange will be here in this line, which is 16.0. Okay, 16.0, which is 16. So check whether it will be less than or greater than 9.4. So if you simplify, you will get around 4.375. So which is less than 9.4. So here it is satisfied, first case. And next one will be, check the web part, D by TW. So flange part will be okay, which was in plastic section only, and web part. See here, for choosing the web part, neutral axis at the mid depth, we are choosing this condition, D by TW less than 84 epsilon. Okay, D by TW for the web part, D by TW less than 84 epsilon. So we know what is epsilon. It will be 250 by 250 square, which is 1. So what about D? So D is, already we know the depth of the channel, which is H. So that is around 400. Okay. So see in the steel. So D will be equal to 400. So we want only web part. This 400 indicates overall I section like this. So what I am telling means, so this is the I section like this. So I am roughly drawing the diagram. So this I section indicates from top to top it will be, sorry, from here to bottom it will be 400. And again, width of the flange will be 140, thickness of the flange will be 16. So width of the flange is 140, thickness of the flange will be 16. So both flanges, it will be 16 and it will be 16. And what is thickness of the web? You can check that one also. That is also important point. for finding web part. The thickness of the web will be, so this is the thickness of the one which is 8.9. Okay, 8.9. So this is 8.9. I am writing here. So therefore, what is D? D means we want only this web part from here to here. So if you want that one, I am taking 400 minus 2 times of this thickness, which is 2 times of 16. So then you will get a overall height of the web. So like that I am taking 400 minus 2 into 16, and thickness of the web will be 8.9, which is less than 84. If you simplify, you will get around this one will be 41.35, which is less than 84. So based on these two conditions, what is obtained? So if it will be then 84 epsilon and less than 9.4 epsilon, means it will be class 1 plastic. So what is your beta B? What we seen in the code book in page number 53. See here, it will be 1.0 for plastic and compact section. For that only we are doing classification. For semi-compact section, you can take down the values which were in the steel tables, which is ZE by ZP. Like that you have to find this one. So for plastic it will be 1.0. Therefore I am taking directly 1.0 ZP into Fy gamma m naught. So here, so I am taking the same formula here after the classifications. 1.0 into ZP Fy by gamma m naught. So what is ZP here again? For finding the ZP, you check the condition in the code book where it will be. So where is ZP? So ZP is given here for ISMB 400. ZP will be given. So in the steel books also there around page number 138. So I am checking there. See here, ISMB 400. Where is ISMB 400? So this line. So purely this line, which is ISMB 400. Okay. So see here, where is ZP and ZD? Section modulus and plastic modulus. So in this line exactly, so it is 1020 and 1176.18. See here, this is ZDZ, ZPZ. The one is will be ZD, which is 1020 in ISA. You please keep one scale exactly here at 400 in the straight line relate to ZD and relate to ZY. So I am taking directly those two values which was in the steel tables in page number 138. So that ZP value will be directly I am taking here, which is 1176.2 into 10 to the power of 3 into Fi will be 250 by gamma m naught 1.1. So if you simplify this one, how much you will get? You will get around the value will be 267.32 kilonewton meter. You please check once. The value will be around this much. Your MD will be equal to 267.32 kilonewton meter. So like this you have to check your values directly in the code books. So I am taking this value which is 1176.18 in the code book directly for ISWB 400. And again, in the page number 53, there will be one formula. See here, we solved this formula. MD will be equal to beta B ZP Fi by gamma m naught. And again, there will be two conditions. To avoid irreversible deformation, under serviceability loads, MD shall be less than 1.2 ZE Fi by gamma m naught in case of simply supported beams. And in case of cantilever beams, it will be 1.5 times of ZE Fi by gamma m naught. Actually, our question related to simply supported beams, and again we have to check with this condition 1.2 ZdFi by gamma m naught. Okay, and again here I am taking that MD will be equal to 1.2 ZdFi by gamma m naught. So all things will be same, just in place of ZD there will be ZP. So we will check same ZD value in the code book in page number same 138. So it is better to write down in the starting itself what is what ZD, what is ZP. See here ISMB 400. So this is ISMB 400. For this your ZD value will be here, which is 1020.1020 value. So ISMB 400 ZD value will be 1020. I am taking that value directly here. So 1.2 1020 into 10 to the power of 3 into 250 by 1.1. So how much you will get? Around, you will get around 275 approximately. So exact value is 278.18 kilonewton meter. See here, we solved MD. One will be based on this formula, which is 267.32 kilonewton. Another one will be MD will be equal to 278.18 kilonewton meter. So out of these two, take down lesser value, whichever is less. So therefore, your MD will be 267.32. Like that, you have to find the MD value. Then next point is design shear strength of beam. So already I solved design shear strength in the first example itself. So like that, you have to follow the same. I will show here also. Second one is design shear strength. So what is the formula in the code book? Check once again here. See here, for design shear strength, the formula will be this one. V will be equal to Vn by gamma m naught. Again, Vn will be equal to Vp. Therefore, take Vp by gamma m. Vp will be equal to Av Fy W by root 3. Av Fy by root 3 into gamma m naught. I am just substituting in place of Vp will be equal to this value. In place of Vn will be equal to Vp. And again, we are choosing rolled beams only, which is H into Tw for Av. Okay. Therefore, the final formula will be equal to H into Tw into Fi by root 3 gamma m naught. This is the formula for finding the shear strength. So I am taking the formula directly here. Vd will be equal to H into Tw Fi by root 3 gamma m naught. So we know all the values in the code book. So you can check once again what are the values. If you know, you can directly take down for IS 400. What are the values? Your H value will be 400. Your thickness of the flange will be equal to 140. Thickness of the, sorry, breadth of the flange will be equal to 140. Thickness of the flange will be 16. Thickness of the web will be 8.9. So whatever the values you want in the formula, you can take down all the values based on the steel tables. H will be equal to 400, which is overall height of the section, into thickness of the web is 8.9. Fi will be 250 by root 3 comma m naught will be 1.10. So if you simplify, how much you will get? You will get around 467.129 kilonewton. So this is the way to find the design shear strength. See the continuation of the question. What the next topic will be: the intensity of UDL that the beam can carry under service condition. So for finding this one, so generally our case will be simply supported case. So for simply supported condition, so we are in third point, intensity of UDL, which is W. Intensity of UDL means we are finding this value here. Okay, what is, so for simply supported case, generally it will be like this. So we are finding this W value here. Okay, so we know what is the maximum bending moment will be equal to mu will be WL square by 8. So what is this mu? What we obtained in the design bending strength. So if you check here, what is the value? We taken out of these two, whichever is lesser, the value will be 267.32. So I am taking that value directly here. That is 267.32. Here the load in terms of ultimate load. So we are solving the ultimate into general load. That is W, keep like that only, into what is the L? L is the effective length of the span, which is given here. So effective length of the span will be 5 meters. Take down the same value here, which is 5 square by 8. So if you simplify, you will get a W value here, ultimate load. That one will be equal to 85.5 kilonewton meter. Okay, so kilonewton per meter, this one will be. Okay, your ultimate load will be this much. How we will obtain this ultimate load? Generally, W equal to factor of safety. Ultimate load will be equal to factor of safety into intensity of load. So if you want W means, what we have to do means, W will be equal to W by factor of safety. So here W value will be 85.5. So factor of safety will be taken generally for service conditions, which is 1.5. So if you simplify this one, you will get 57 kilonewton per meter. So this is the intensity of UDL on a simply supported beam. That is 57.7 kilonewton per meter. So that is the value which is W. So your third point. Next one will be deflection. See here, maximum deflection. So after obtaining this one, your next topic is maximum deflection. Fifth one, sorry, fourth one, maximum deflection. So how you have to find this maximum deflection? There will be one formula for simply supported conditions. Generally, we learn all these things in strength of materials itself. So that one will be equal to pi by 384 W L power 4 by EI. So what is this W? That is intensity of UDL. What we find now? That is 57 kilonewton per meter into length of the span will be 5 here, which is 5000 with in mm. 5000 in mm. Here generally this 57 also in kilonewton per meter. So for obtaining kilonewton per mm, take down into 10 to the power of 3. Okay, and E value will be 200 kilonewton per mm square. So all the values we are taking in mm. Okay, and what about this I? So check the I value here in the code book itself, steel books. So it will be IXX. The value will be 20458.4 into 10 to the power of 4 in mm power 4. Okay, so IXX or IZZ. Take down this value 20458.4 in 10 to the power of 4. Simplify the values, totally the deflection will be obtained in mm. Okay, so you will get around 11.34 mm. So therefore deflection, maximum deflection will be 11.34. This is the way to find the maximum deflection. So for thank you so much for watching this video. If you really like this video, please like this video, share it to your friends and subscribe our channel. Thank you so much.